Live, going live. We're live. Hello, world. My name is Alan. We're doing LeetCode practice. This is the third problem for today, and it's medium level problem. And let me share what it looks like. So this starts. So this is one of the problems while it's loading. It's one of the problems about a heap data structure. And I just recently learned that the heap has implementation in the standard library of Golang. In Go, yeah, I haven't seen it before. I haven't been noticing. Package heap provides heap operations for any type that implements heap interface. A heap is a tree with a property that each node is the minimum valued node in its subtree. The minimum element in the tree is the root. Okay, so this is a min heap. A heap is a common way to implement a priority queue. That's the heap we have in our standard standard library. So to build a priority queue, implement the heap interface with the negative priority as the ordering for the last method. So push adds items. So I haven't looked how to use that package yet. It's in the package container. So standard library, package container has heap, list, and ring. And heap package heap provides heap operations for any type that implements heap interface. I'm curious. Provides heap operations. So we would need to have, ouch, the heap, create a type. So how does that work? That's more than 2 lines. Okay, it's restart the clock. So why is it important to use this, to learn to use this, or to be able to use this package? Because implementing a heap like doing this implementation yourself is gonna be, I don't think it's with, I'm not sure if it's like, if it's within, if it's interview standards format. Yeah, it's probably longer than an interview can. You can do in an interview. So it's good to know. So part of this exercise today is to learn to use that, see if I can use that package. And the other part is to solve our problem at hand with that package. Well, let's just quickly look at the problem. Given an integer array nums and an integer k, return the kth largest element in the array. Okay, note that it is the kth largest element in the sorted order, not the kth distinct element. Can you solve it without sorting? Yeah, because the sorting obviously is easy, but yeah, like to sort, yeah, the fifth, the second largest will be largest element. K is 2. So 6, 5, yeah. Okay, so we need to find the largest, then the second largest, K, yeah. In this case, okay, so 4, and we'll have fourth, yes, so 5, 6, 5, 6, 5, 4, 3. Wait. Oh. Okay, no. 5 is repeated. So 6, 5, 5, 4. Okay. Alrighty. Here is the problem. I mean, if we use a heap, which I don't know if you can use duplicates in a heap. I'm not sure. Because heap data structure, look at the map. Yeah, I don't think you can use duplicates because in a heap, every root, yeah, the root is a heap is a tree with the property that each node is the minimum valued node in its subtree. If they're not distinct, if the values are duplicates, can you have duplicates in a heap? Heap data structure can heap data structure have duplicates? First, we can always have duplicate values in a heap. There is no restriction against that. Second, a heap doesn't follow the rules of a binary. Wow. In duplicate values. Yes, but I would say no. For efficiency, they shouldn't have different nodes with duplicate values, or it loses its purpose a bit. Okay, so it actually can have duplicates. Okay, that's fine. Well, then what we need, if we need to have, like, how do we find the kth element in an array without sorting it? And by the way, we have 10 to 5 overall numbers, and their range is 10 to 4 to 10 to 4. So my first thinking is the simplest way is to do counting sort, which is kind of sorting, or the frequency array. Yeah. And then we'll start with the largest ones and just count them. And that will use some memory, but that will also topics, divide and conquer, sorting, heap priority queue, quick select, topics, yeah. But that will also so this kind of sorting, and I mean, the array that we will need is gonna be at max is it's 10,000 plus positive 10,000, right? And negative 10,000. So the range is essentially 20,000. Yeah, so we need an array of that length, and we're fine. We can use counting sort. So that's my first counting sort. But since this is a non-sorting, this is like use heap, which is kind of sorting also. But yeah, how would you use a heap? If we put all these numbers into a heap, that would give us like then we just need to pop the root of the heap, rebuild it again, and pop, just k times we pop it and rebuild it, which is filling up the heap is itself is we fill it up first, but then what's the word when you rebuild it, I forgot the word, but push. Yeah, what are the operations they use here? Pop. When they pop, function pop. Pop removes and returns the minimum element according to less from the heap. The complexity is log n, where n h length. Pop is equivalent to remove. Removes and returns the minimum element. Here we have remove, we have pop, we have init, and it establishes the heap invariance required using this package. Fix reestablishes the heap ordering after the element I has changed its value. Changing the value of an element at index I and then calling fix is equivalent to less expensive than calling remove, followed by push. The complexity is equivalent but less expensive. Okay. Okay, so basically we just need to do what's called a pop. Removes and returns the minimum element. Yeah, so we need to do pop k times, and that will give us that element. So priority queue, int heap. This example inserts several ints into an int heap, checks the minimum and removes them in order of priority. Removes them. Heap. Heap init, heap push, print minimum, heap length. Okay, and then the next example, just checking out the standard library heap package in Go, standard library, yeah. This example creates a priority queue with some items, adds and manipulates an item, then removes the item in priority order. So the main function, priority queue, put the item in it. Okay, the first example, I guess, would be fine for us. Int hip, yeah, because that's what we have an int hip. Yeah, so another one is hip pop k times. Yeah, the first time will be the biggest. The second biggest is after the popping for the first time. Yeah, so this this solution is pretty obvious. The counting sort. The hip solution is something I would need to try and see if I can actually do it here. What solutions did people do? Hip and quick select and sorting. Wow. I don't even know what quick select is. What is quick select? Quick select algorithm. Quick select is a selection algorithm to find the kth smallest element in an unordered list. It is related to the quick sort. Oh, okay, sorting algorithm. In computer science, wow, there is this. Check this out in computer science. I like how it starts. Quick select is a selection algorithm to find the kth smallest element in an unordered list, so known as the kth order statistic. Like the related quick sorting algorithm, it was developed by Tony. Okay. And thus is also known as the Horse selection algorithm. Like quicksort, it is efficient in practice and has good average case performance, but has poor worst case performance. Quickselect and its variants are the selection algorithms most often used in efficient real-world implementations. Wow. Oh, animated visualization of the quick select algorithm. Selecting 20-second smallest value. Partition that can linear time group a list ranging from 2 parts. I did. So, what's the purpose of this? Kth smallest. Find the kth smallest element in an unordered list. Oh. Okay, kth smallest. Okay, it looks like the guys, they did it in like multiple different ways. So they did it in several approaches. Sort and select, okay. Min hip, all right, that's what quick select algorithm. Gee. And performance, and go, performance, yes, so code, performance, hip, okay, that's the code, the go code for the hip. All right. and then the quick select. Okay, the pivot and all that. Got it. Okay, so basically we looked it up because yeah, because we're just kind of I'm introducing myself to how I like to do the hips here. And my thinking is that the counting sort is not the worst, because I mean, in terms of time complexity, the runtime, yeah, the counting sort is gonna beat all of it. It's linear. It's not linear. It's gonna be like a billion. You'll need to go through, where is it? The range. Yeah, I need to go through the range, through that range, not 10 to 5, but actually you'll go to the 10 to 4s in this case, because the range here is 20, yeah, 10 to 4. In this case, it's faster. But if we want to learn to use the hip, which is that, I think I should look through how to do it. So they import the hip, yeah, and then just they create. You see, there's like type and like bunch of methods, and then they use these methods. So it's using that. It involves you using that. Using that package hip. Yeah, I would say I would need to practice it to remember like how to use the package hip. Yeah, I would let me do this. Let me try to implement the counting sort. Yes, it will be and yeah, let's see that, because what's curious about it, it's faster than, it's like linear time. By the way, quick select, they say is okay, worst case is n square. Our worst case, and it depends on what you call worst case, but it could be much worse than n square. It depends on the range. If the range is like, if the range is huge, yeah. Let's do counting sort, and maybe next time we'll do the hip. Yeah. So because counting sort is gonna be the best in terms of time. Should be. We'll see. So basically, we're dealing here with offset, because we want to fit. We want to have an array that frequency array, which is a slice, and make slice of integers, which is going to count. So it's gonna be like minus 10,000 to positive 10,000, which is, if I'm not mistaken, is 20,000. So we'll need an array of the length one of this length. This, yeah, 10 to 4. By 2. plus 1. Yeah. So 2, that's the length that we're gonna need. 2 plus 1, because, yeah. And we will have an offset of a const offset is gonna be 10,000. So when we get a value, nums value, we're gonna go over it's 10 to 4, yeah. So we have it, yeah, we don't worry about the index, but the value, range nums. So I'm gonna say that in this frequency array, at this index, we need to count them. Yeah. So but we're gonna use our offset to plus offset. Because if it's minus 10,000 plus 10,000, we're going to get a 0. 0 index, yeah. If it is plus positive 10,000, we are going to add 10,000. We'll get 20,000. And plus 1 is gonna be the index, yeah, for it. So that should be enough. What else do we have here? Yeah, now we're gonna go for I is going to be length of, oh no, oh no, oh no, oh yes, oh, it's all good, it's all good. So we're counting how many of those, of each number we have. So for length of frequency array, I is length of frequency array minus 1. So it's the last one because we want to start with this, with the largest. And now we're just gonna go, because there might be multiple elements, repeating elements. So we're just gonna go until, yeah, like iteratively, I is bigger or equal to 0. There could be zeros, yeah. I minus. And by the way, we need to do that k times. So so we're gonna go like the first time we're gonna get the largest number, yeah. So gonna say that answer, by the way, we're gonna say answer is 0, and we're gonna say that answer is our frequency array at I. But we actually need to go until k k could be, yeah, k, and k is bigger than 0. So we start with k1. We read answer. We say k. If k, like the smallest, is 1, yeah, and then we just return answer. So that's kind of it. So once k is 0, we're out. Yeah, so this should be working. Output is 0. Output is 0. For k is bigger than 0. For so k is 2. Oh, wait a second. We need to do that only if that is not 0. Yeah. So, okay. First, we'll look at that. If that number is more than 0, then we remember I. Answer is I. And we reduce, so we read it. We read the count, minus. Yeah, so that should be it. And by the way, no. And then k is also only reduced if that's the case. Yeah. Otherwise, we just go to the next. And by the way, we don't want to change. Oh, gee, yeah. We don't move the index until we're out of this. So we move the index when it's 0. Yeah. So wait a second. If it's more than 0, we don't move the index. Else we move the index. Yeah. So okay, we check what's the last one. And if it's not 0, yeah, if it's more than 0, we say, okay, now that could be an answer. And then we say, okay, we read it and we count it and go try again. Now, if it's 0, we go to the next one. Yeah, so this should be working. No. What? 10,005. So in this case, there is 6. Oh, well, it's 10,000. Oh, gee, we forgot the offset. So the answer, yeah, these indices, the answer is that index minus the offset. Yeah, minus the offset, finally. Yes, so we are at the top with the speed. Memory-wise, not the best memory, not the worst. Somebody used something. Well, they figured out the min and the max, and then they build the count with the length of that range. Yeah, with that offset. And by the way, they just moved the count like by all these. Yeah, so yeah, that's I like that. I like that structure. Yeah, you don't have to go by one. Once you see, oh, look at that! Look at that! That's so cool. So if k is 0, just return. Oh yeah. So basically, so that's so easy. That's so sweet. Yeah. So what he does is like, okay, we are going to go each element, but that's an integer, and k is also an integer. So why don't we say, okay, if there is not a 0 in this, yeah, we're just gonna deduct it from the k. But when k is actually when k becomes 0, that's what you need. Yeah, return. Yeah, return that, because that's all you need. That is all you need, because yeah, because just reduce k by that number. So yeah, and once we hit the 0, we're out. Nice, 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 nice. Well, yeah, it's more optimal because they figured out the range and then built the count array based on that. I think it's a pretty good solution, and it's probably one of the, I don't know, most efficient ones for this one. Counting sort. Yeah, so that's yeah, we can practice with the heap next time. We probably will need it. But this is a good I just like the counting sort so much, just because of its linear, well, linear comparing, referring to the range. Yeah, based on the range of numbers. So it's just can you solve it without sorting topics? Sorting, quick select, heap, sorting, divide, and conquer. How can you do it by divide and conquer? Is that the quick select thing? Divide and conquer. Because this solution, I don't think it had divide and conquer. Well, maybe in some way. Maybe in some way. Performance, min hip, Rust, performance, Java is so performant. Look at that. For some reason, Java is like more performant than Rust. I don't know. I don't know, but well, so I guess that's a good third problem that we solved today. Yeah, we might want to practice with the hip a little bit next time. But for now, that's our third problem. Medium level. Thank you for watching, and see ya.